And we are super delayed, but the last highlight poster talk from this session, and I would like to invite Yurii Pershyn. And he is representing X-ray optic production group in Ukraine, in Kharkiv, Polytechnic University, and we are welcome you for your brief talk.
It is visible.
Yes, yes, yes.
So I present the information about our activity, particularly multilayer coating for synchrotron radiation. We have 40 years experience in the multilayer fabrication and study, in particular reflective X-ray mirrors. They're a multilayer coating, usually periodic, of at least two materials deposited on a substrate. The layers are about a few nanometers thick. One of the layers is low absorbing material. In the soft X-ray region, they have a reflectivity of tens of percent. This picture shows the list of multilayer we have made. The following are some recent results on application of fabricated multilayers. So the first application is multilayer for radiation-resistant materials and in nuclear and thermonuclear power engineering. We proposed for this application multilayer materials composed of tungsten and quasicrystals. Tungsten is used as plasma phasing materials due to small sputtering rate, high melting threshold, and high heat conductivity. However, due to the gradual accumulation of light isotopes, for example, deuterium, tritium, internal macro stresses develop in this material, leading to the formation of surface cracks. Titanium, zirconium, nickel quasicrystal can function as reversible hydrogen absorber in solid solution form without hydrogen formation and subsequent hydrogen release. In such layered system, quasicrystal reduce the effect of hydrogen on tungsten. The multilayer, as can be seen in this figure, retains its layering even after annealing at 700 degrees of centigrade. So we can see that at temperature of 600 degrees, it is begin degrading, but at 700 degrees of centigrade, some layering is consumed. This small angle diffraction curve for multilayer annealed at 500 of degrees centigrade. So we can see that it is quite good, have quite good layering, and by red it is represented fitting curve, which allowed us to get some characteristics of layering materials represented in the tables. And that is thickness of multilayer, their density in interface roughness. The second application is reflective multilayer X-ray masks. So X-ray lithography uses shadow X-ray mask. They're very thin, and absorption of X-ray in this mask may be the cause of distortion, delamination, or even breakage of the X-ray masks. So we offer reflective X-ray masks that are free from the most of the disadvantages inherent in shadow X-ray masks. So in this figure, it is shown the principle of application of reflective X-ray mask. So multilayer applied on the thick substrate, and grazing incident of X-rays allows to compress the pattern applied on the reflective X-ray mask to compress in the resist plane. In this figure, it is shown that how this process occurs. On the figure B, on the figure A, it is shown electron microscopy grid, which we use to form absorbent pattern on the surface of the carbon tungsten silicon multilayer, through which we deposited tungsten layer, absorbent tungsten layer, 2.5 micron thick. At 4 degrees grazing incidence for synchrotron radiation, we get compressed image, which is shown on the figure D, and magnified image of the part of the B is presented in the figure C, and we can see that several microns of elements can be resolved in the resistant resist plane. Usually crystals are used as monochromators for X-rays, but they have limited application due to small D space. So they cannot be used for the wavelength range longer than 2 nanometers, or energy it is shorter than half of keV. Organic crystals are used for this wavelength spectrum, but they have low reflectivity and low stability. Multilayer combine the advantages of both type of monochromatic. So we fabricated tungsten boron carbide multilayer with period, which is the thickness of 2 layers, tungsten and boron carbide, around 1.3 nanometers. Reflectivity, which we have copper K alpha radiation more than 30%, and resolution around 400. The right figure is cross-sectional view in transmission electron microscopy, mainly this sample. Another application for high-resolution mirror was made at Bonn University. It is tungsten silicon multilayer, and we characterized this type of multilayer at the wavelength around 2 nanometers, and get resolution power around more than 200. So thank you for your attention. Any questions?
Thank you for brief talk. I guess if there are any questions, we can make them via like mail exchange because we are really behind the time.